Okay, so we're going to start with the ice melting contest, which is lab 2. And I'm going to start with this jug of water, right? It's the same water. I'm going to fill both of these beakers about the same amount. And you guys are going to, I didn't mention it, but you're going to need some colored pencils. And then for this one, I'm going to put a bunch of salt in there. And the other one, I'm going to leave it alone. So we have fresh water that came from the same container. We have about the same amount of fresh water, but one of them has salt in it, right? So it's salt water. And then if you look at these ice cubes, would you agree that they're basically the same? Yeah. Okay. So these ice cubes, the only thing about them is that, let's see, I wonder if you can see that at home. The only thing about them is that they have blue food coloring, just so we can see the cold ice cube. Okay? So to start with, on your paper, you should start by making a prediction. Make a prediction of which one you think is going to melt faster. The cube in the fresh water or the cube in the salt water. So which one is going to melt faster? Predict. And again, it doesn't matter which one you predict, because your grade isn't based on whether it's right or wrong, yeah? It's only based on thinking, really, and participating. So here's our salt water and our fresh water. Let's see. I'm using this over here. Will somebody get out a stopwatch on their phone for me? And are you ready?
Yeah.
Set, go. Okay, so while those are melting, let's go ahead and work on the next couple questions on the worksheet. First of all, number 2, name the variables. And we've got the independent variable, the dependent variable, and controlled variables. So the independent variable is the cause of any differences. It's the one that I set up to be different. So what's the independent variable in this case? What about it?
Salt.
The presence or absence of salt, huh? Fresh water versus salt water. This is a definition of it. I want to know in this lab, what is the independent variable? The cause of any differences that occur would be whether or not it has salt, right? Salt versus fresh. That's the independent variable. And then the result, or the effect, is the dependent variable. So what am I going to measure at the end and compare? What effect am I looking for? What are we measuring? Actually, Kate is helping me out with that. What's he measuring?
Time.
Time to
Melt.
Time to melt. The melting time is the dependent variable. Does it depend on whether there's salt present or not? That's why it's called dependent variable, because it depends on the independent variable. Does that make sense? I think of them as cause and effect. And are we starting to see any differences yet? Like, I see a lot of blue down in this one, scattered throughout the entire beaker. What's the blue looking like here? Can we see it?
Just on top.
You say it's on the top?
Mm-hmm.
Okay. So that's something to watch for, where the blue ice water is going. Okay, and then we have controlled variables, and I've asked for 3 of them. A good experiment has many controlled variables, and these are things that we keep the same, that we keep constant, so that we can make sure it's a fair experiment. So what things did I keep the same here? We want to list 3 different things that were identical on both sides. I kind of pointed it out while I was setting it up. For example, did we have different sources of water, or was it the same water? Was it the same starting temperature of the water? That might be pretty important. Would it be fair to start one with warmer water than the other, and then say that it was because of salt that it melted faster or not? So the same starting temperature is a really important one. What else did I keep the same in there? What else is constant between these two? The amount, yeah. The same amount of water. And I'm not stirring either one, am I? So as long as I'm keeping that the same. All right, we just finished melting the fresh water.
Should I stop it?
No, to keep it going, and we're just going to round that off to 3.5 minutes.
Okay.
What else did I keep the same? Same volume, same starting temperature. How about the ice cubes? Were they identical ice cubes? Pretty much. They both had blue food coloring in them. But other than that, they were about the same size. So the fresh water is our winner here. And now, I want you to look really closely at what the blue is doing here. Is it forming a layer on the top? Whereas, did this one make a layer on the top? This one has no layer, huh? Excuse me, this one has no layer. It's all pretty much evenly distributed. In fact, you might have seen the blue sink down to the bottom at first, huh? But here, all the cold is concentrated. And I'm going to zoom this camera in there for a second just so we can see that on for somebody that's not here. I can do this. Yeah. There we go. We can see that that one has a layer and this one does not. So if you guys ever can't make it to class on a day that I do a lab, look for a film of it on YouTube, which I will post the link to, all right? Okay, so let's think about that. Is it melted yet? Not quite. Just going to move it around just to see it. Yeah, it's not quite melted yet. So why is this one melting more slowly? What do you think is causing it to melt slowly? Okay, so what temperature is that blue water? The blue water is all coming from the ice, isn't it? So it's cold. And what happened to the blue water in the fresh? Kind of went everywhere, huh? What happened to the blue water in the salt? It stayed at the top. And isn't that where the ice cube is? So if this is a layer of cold water at the top, doesn't that kind of protect the ice cube and prevent it from melting for a little while at least? Right? But why did it make a layer in this one and not in the other one? Why is there a layer here?
Salt water will make dense.
Do you remember we measured the density of fresh water versus salt water? And the salt water had a higher density, didn't it? So that means the salt water stays underneath the fresh water. The fresh water is like floating on top of the salt water, isn't it? But that fresh water is cold, so it protects the ice cube from melting. It's because of the density difference between salt water and fresh water. Here, this was the same density as the ice cube. As it melted, the cold water spread out, and that allowed the warm water from the beaker to melt that ice cube faster. Okay, where's our time now?
7 minutes and 30 seconds.
We're almost done with this guy. There's still a little tiny bit of ice there. Does that make sense? What I'm talking about? How the density of the salt water kept the fresh melted water at the surface, which kept the ice cube cold so that it didn't melt. Okay? So you need to write out an explanation, and you need to use your colored pencils to draw. We need to label which was salt and which was fresh. The one with the ice cube in it would be the loser. Okay, now we're good. Let's just call it 8 minutes for the salt. So color in those diagrams. Record the time when they melted, and label each beaker, which was the fresh water, which was the salt water. And did you see like blue kind of dripping down through here? So maybe you want to draw some arrows to show that movement in the fresh water. Whereas in the salt water, you just pretty much make a layer of blue at the top, huh? And then write out your explanation for what happened. And you should use some phrases like density, layers. I don't know if protection is a really valid word, but that's the way I think of this layer of cold water on the top of the salt. Kind of protected the ice cube from melting. And then let's think about this. If there's an iceberg, it broke off of a glacier from land, right? So it's fresh water, and it floats out to sea, and it takes a little while for it to melt, doesn't it? But imagine that ice melting out in the ocean. It's freshwater ice. Can you imagine that in a way there's like a pool of fresh water sitting on top of the seawater. Does that make sense? You could almost imagine that, at least for a little while. Now eventually it'll all get mixed, just like the salt water with the blue layer. By tomorrow it'll all be equal throughout everywhere, because there's nothing keeping them separated, huh? So it's just a temporary thing. Eventually they'll get completely mixed together. Yeah, we're going on to lab 3 now, and we call this the liquid wrestling match. And our first 2 contestants is the green versus the yellow. So what I'm going to do is I'm going to fill up one side with green, fill up the other side with yellow, and then I'm going to take this divider out and they're going to mix. And one layer is going to end up on top of the other. So I want you to start with a prediction, and I'm not really going to give you any more information than color. Predict which one you think will end up on top, or which one will end up on the bottom, or maybe you think that they'll just have an equal mixing. So what do you think is going to happen with this first wrestling match? Okay, so are we ready? I have to do this kind of quickly because they start to seep underneath. This little divider here isn't perfect. So I'm going to get going. Here's the green. Here's the yellow. Yeah, and then you're going to do the before drawing would look like this, right? 3, 2, 1. What's going to happen? So what did we end up with there? Which one won? The green? Yeah, that's because that's the Highlanders color, right? So, yeah, the yellow formed a layer underneath the green. And, of course, now the next question is, why do you think that happened? Why did the yellow end up underneath the green? Any hypotheses about that? What do you think? Explanations. It is the density again. Totally density. And what did we just learn in the previous one? There's one other thing I did to one of these solutions besides the food coloring. What do you think I did to it? What did I show you a minute ago? Because it was heavier, it went to the bottom? Or it floated on top? What was the difference with the one that had the layer in the ice cube? The salt, right? So what do you think here? The yellow is... What do you think? Is it salt water or fresh water for yellow? And the green is? Switch that around. Salt is denser. So the salt water is on the bottom. And the fresh water is on the top. So you should have an explanation there, right? And you need to use terms like density and layers. Which one's more dense, which one's less dense. And we're going to do it again with 2 other liquids. Red versus blue. And once again, I'd like you to make a prediction of which one you think is going to end up on top. Okay, I'm going to set it up. You guys are coloring, I see, as we go. That's great. Blue on one side, red on the other. Here we go. 3, 2, 1. Might be better in the future if I have more, huh? If it's filled up to here, it's easier to see, I bet. So what's happening? Are we getting layers? And which one is going where? And why do you think that is? And I will tell you that it's not salt this time. Exactly right. It is temperature. So which one do you think is warmer? So just to show you what I used, feel that, the bottom of it, and be careful with this one, but feel that. Right? So this one was, which one was blue and which one was red, do you think? Which was the blue? Last class I flipped the colors. But yeah, this one in this jug had been in the refrigerator overnight, and I colored it blue. This one I heated up for about half an hour before you got here. It was almost boiling. And I colored it red. So what happens with the speed of the molecules when you heat something up? The molecules in the liquid are moving around, right? They're moving around, and then when you heat them up, those molecules end up moving faster and faster and faster, and they move further apart. Now, if the molecules are further apart, what does that tell you about their density? So imagine, here's these molecules when they're cold, packed together. Here they are when they're warm, spread apart. They expand a little bit, don't they? And when they expand, their density goes down, less density, which means they float to the surface because they're less dense. And there's several examples of the way this happens in nature too. So for lab number 4, we're going to actually do something a little different. I'm going to do a diagram on the board for this one. Sorry about this filming business. I just want to make sure people who can't make it are able to make up the lab. So, okay. So, we're going to do a diagram over here. And we're going to start with the Earth. So this is the surface of the Earth curving around. And then we're going to put the sun up here. And the light waves are making their way towards the Earth, aren't they? Okay, so when we look at this, will every point on Earth get the same amount of heat as every other point? No, which will get the most? Right underneath here, huh? Directly in line with the sun. Instead of having to come in at an angle, it's coming straight down, isn't it? And making it hotter there, right? So this would be like the equator. We're looking at the Earth sideways here. This would be the equator. These would be the poles. Okay, now think about this. What happened to the warmer liquid? The warmer liquid, did it have more or less density when it was warmer? Had less density, right? So it floated upwards, which is the same reason you might have heard that what does hot air do? Hot air rises, right? And so right underneath the sun here at the equator, we're going to have rising air. The hot air is going to rise because it's less dense than the surrounding air. Okay? But wait a minute. If this air is rising and leaving the Earth, doesn't that mean we've kind of created a vacuum there? Haven't we created a void that needs to be filled? And so air on the surface moves in to take the place of the air that rose up. And this movement of air is what we call, of course, what do you call it when the air is moving past you? Your hair is blowing in the wind. This is the cause of wind, is this movement of air to fill the void left by rising air. Well, eventually this air gets high enough that it can't rise any higher, and it spreads out to either side. So the air is spreading out to either side when it reaches a certain point in the atmosphere. And as it's spreading out, it's cooling down. And just as the hot air rises, the cool air must sink back down. It must fall back down, huh? So do you see how we have these two cycles here? Where we have hot air rises up, it spreads out, it falls down, it comes back to the center again, making wind along the way, gets heated up, rises, spreads out. Now this would also be wind, but it's up high in the atmosphere, so we don't really experience it unless you're in a plane. Spreads out and it cools off, so it sinks down again. Right? And we call these convection currents. And specifically, we have, in the way I've drawn this, we have two convection cells. We have two interlocking convection cells where the air is kind of moving in opposite directions, huh? But the air is always moving towards the hottest spot where the air is rising, huh? Hot air rises, spreads out, cools down, falls, and the wind brings the air back into that beginning point, right? So this is what I mean by a convection current. It's because of the difference in heating versus cooling, and it's because of the change in density as a result of the heating and cooling. So we have one more little demo here. And this one, I'll bet you'll be able to predict what's going to happen. So I'm going to take this little container, I'm going to put some room temperature water in it. And here's a vial of water that I kept in the refrigerator overnight. And then I'm going to take another vial of this heated water. And I'm going to color that red again. And I want another background for this. It's easier to see. Okay, so here's what I'm going to do. I've got this hot water in that's red, and I've got the cold water that's blue, right? I'm going to lie these down in here. And then I'm going to take the lid off. What do you think is going to happen? What's going to happen to the red water, the hot red water? It should rise, huh? And what's going to happen to the cold blue water? It should stay on the bottom, right? Now, if I had a continuous heat source for the red, it would actually start cycling through there like we were talking about with a convection current. Come on off. Let's see if it happens the way you predict. So is the red rising upward? And what's the blue doing? So we're kind of starting a convection current here, aren't we? Where the red rises up to the surface because it's warmer, which means the molecules are more spread out, which means they're less dense, so they float. It's kind of like a whole chain of cause and effect, huh? You start with the heating, that spreads the molecules apart, that makes them less dense, so they float upward. And just the opposite for the blue one, where it's cold, so the molecules are more packed together, so it's more dense, so it sinks to the bottom. Okay. And so did we take care of everything on lab 4? We're done with that? Let's go back to number 1 then, which is a video of these lava lamps. Have you seen lava lamps before? Okay, so now that you know about the influence of temperature on the density of something, can you explain how the lava lamp works? We're going to want to do a diagram. We want to do a drawing. So at the base of the lava lamp, we should show that it is, there's kind of a little circle at the bottom of your diagram. That should be a heat source. That's the lamp itself at the base. So you want to label that. It's like a heat lamp at the bottom. All the way at the bottom. Yeah. And so you can tell that we have 2 different liquids in here, right? There's the surrounding liquid, and then there's these blobs that are rising up through it. So those blobs are wax, and when you turn on the lava lamp, it melts, right? And it gets hot, so what happens to its density when it's hot? If it's hot, the density becomes what? More or less? It becomes less, and so when it's hot, where's one that's rising? The red one over there, or that one, or this green one. When it's hot, that blob rises upward because it's less dense, huh? But once it gets up there, it's away from the heat source, and it cools down again, and it becomes more dense and sinks. And we have this full-on cycle of convection currents within each lava lamp. Now, why do we call it a lava lamp? Well, because it's mimicking what's happening inside of the Earth. So think about the interior of the Earth. That's what we're really studying in here, isn't it? So if we think about the inside of the Earth, it's got magma, and where the magma is getting heated, it becomes less dense and rises upward, huh? And then in other areas, the magma is cooler, so it's going to sink down. And we actually get a convection current of magma underneath the Earth that is just like the convection current we drew a minute ago on the board. So the hot magma is rising up, and then it spreads out underneath the crust. And it cools off and sinks back down again, where it gets heated, so it rises up again. Spreads out, cools off, becomes more dense and sinks. It gets heated again, becomes less dense, rises up. But what I really want you to think about is what's happening when it spreads out at the surface. So the magma comes up, and it doesn't make it to the surface. It's underneath the crustal plates, right? The magma is underneath the crust. And when it spreads out from one side to the other, it's going to drag the continents along with it, huh? It drags those plates with it. So it's the cause of plate tectonics. This whole thing we've been talking about with convection currents right here and the density changes, it's all to help us visualize how the plates are moving. And it's because of convection currents in the mantle that the plates are getting dragged along. As they get warmed, they're less dense, they rise up, and when they spread out, they drag us with them. So if you want a free trip to Alaska, all you have to do is go to LA and wait about 50,000 years, and you'll end up in Alaska. Because the convection currents in the mantle are really slow. So they might, the rising magma might make it a foot in a year. And then when it spreads out at the surface, it might make it, 10 centimeters in a year or something. So it's a very slow process, but it's pretty unstoppable because it's huge amounts of material that are moving. Okay?